So now let's look at the next section, which is on multiples and divisors, primes, and z. These hooks. So which of the following integers are in a set 6z of integral multiples of 6? And we have a few numbers here. But yeah, 6z means these are integral multiples of 6. So negative 12 is in 6z. I mean, it should make pretty obvious this one especially, but basically these are pretty obvious. But a little bit of, just the tiniest bit of showing a little bit of it, because that's what this is meant for. This is abstract algebra. We're not just saying, oh, this divided by this equals that. We're trying to look a little bit into, trying to make it look fancy and all that. So, if negative 12 equals 6x is what it means. Basically, this is in 6z, negative 12 is in 6z, if negative 12 equals 6x. X is in z. So x equals negative 12 divided by 6 equals negative 2, which is in z, so it's in z. Negative 12 is in z, 4002 is in 6z, if 4002 equals 6x. X is in z. And 4002 divided by 6 is equal to 667, which is in z, so x equals 667, so x is in z. Basically, that's in z. It's an integer, so 4002 is in z. Oh, quick note. This should be is in 6z, not z. That's just a minor correction. I mean, you can just do that for your own if you're taking notes out there. You basically this would be, the end result is negative 12 is in 6z. 4002 is in 6z. Because obviously they're in z, they're an integer. But 6z, it's a multiple of 6 basically. So ignore that. It should be is in 6z. Basically you're just proving it, showing it. And then 4003 is not in 6z, because 4003 equals 6x, x is in z does not work. It equals, basically, it's about 667.17, which is not in z, so this would not be in 6z, but it would be in z. But 4003 is not in 6z. It's an integer, alright, but it's not a multiple of 6 integer. So 2, just one part of 2. We're going to try to fit p into 1 plus 6z. Find out which integers of p are included in 1 plus 6z. And these are all the numbers up here, including 17. I wouldn't write that, but just imagine, so, 2, 3, 5, 7, 11, 6, 13, 17, 19, 23, 29, 31, 37. 1 plus 6z, which ones of these are included? It's not all of them, definitely. But basically, 1 plus 6z means 1 minus 12, 1 minus 6, 1, 1 plus 6, 1 plus 12, in both directions. Keeps on going on. But yeah, let's say A is equal to that. And so P intersection A, I'm going to just write it a little bit fancy, how I would maybe write it. So P intersects A. Set P into A at 7, 13, 19, 31, 37. So those are what's included. From what I could tell, that's all. Because, it's basically negative 11, negative 5, 1, 7, 13, and onward in both directions. But yeah, 1 plus 6, 1 plus 12, 1 plus 18, 1 plus 30, 1 plus 36 is what these are. 1 plus 6 times 1, 1 plus 2 times 6, 60. 1 plus 3 times 6, 1 plus 5 times 6, and 1 plus 6 times 6. That's one way of thinking of it, the 5 numbers that made it in there. There's no 25 in here, so I skipped. Is 2z the set of all even integers? Is 0 an even integer? And the answer is yes to both. This is just a fact, basically. But yeah, 2 times basically an integer is a set of all even integers. Because all even integers can be divided by 2 is another way of thinking of that. But is d divide 0 for all integers d? Explain. And these are just short explanations about some facts. Yes. Since 0 equals d times 0 for all d is in z. Basically, you can write it out in one of the proper ways for a divisor. It can be written out as 0 equals d times 0. So if d is a divisor of a number on the left side, it's now equal d times a number. And no matter what, 0 times d will equal 0, no matter what d is. And now list all the integers of 0z, that is, of dz with d equals 0, and this one's very obvious, it's just 0z equals 0, the set of 0. 0 is the only number in that set. What is the only integer m with 0 divides m? Okay, so it's basically saying that m divided by 0 basically, technically, for this subject, this is a true statement, but hold on. 0, it's the only one that could work hypothetically. I think you can admit, even if it doesn't make the most sense, 0 divided by 0 might be the best. And this is because the logic behind this is d divides m implies m equals dn, so 0 equals 0 times n, since 0 basically 0 divides 0, because you can basically you could form in that form of a number equals a number times a number, basically. 0 is equal to 0 times any number, any integer in this case. So that's how that is. I know it's weird, but just hang in there. Is d and dz for all integers d? And I have to explain this one. So yes, this one's quick. Due to d equals d times 1, and 1 is at b and in z. So yeah, it's basically the explanation. It's d multiplied by a number will equal d, number by number 1 will equal d, and 1 is in z. This part is n divides n for all integers n, and I have to explain. Yes, n equals n times 1, n and 1 are both in z, basically is what I'm saying here. It's a simple definition of a divisor, and multiple is what we use in Philotas. Does d divides m imply that negative d divides m? Probably one of the more tricky ones out of all of these. It's true, yes, but basically because d divides m implies that, basically means m equals d times n is in z, and from there you can say that this m equals negative d times negative n, because that'll give you positive m still. You make d and n negative. This implies that, negative n is in z, so that means that negative d divides m. We're just really messing around with basic things. Finally, is 9z, for this type of problem, is 9z basically a subset of 3z. That's one way of saying this. And subset means it's part of the bigger set 3z. Explain. So m equals 9n is in 9z. We basically said equal to that. Then m equals 3 times 3n is in 3z. We can make it 3 times something, 3 times 3n basically. And that'll be included in 3z, basically always. So therefore it is a subset. In other words, every multiple of 9 is a multiple of 3 basically. Which makes very much sense when you really consider it. 9, 18, 27, all these can be divided by 3 as well. And when you multiply anything, you can get basically, which means that you could multiply 3 times the number equals some, which is what a multiple is. Last idea for this section is we have the equation xy minus 10x plus 2 divides y equals 228. Tabulate results. X, y is in z for these, for this equation. But yeah, basically xy plus 2, 21y is equal to 228 plus 10x. Because I added 10x and then I distribute out y, so x plus 21 times y is equal to 228 plus 10x. This implies that y equals 228 plus 10x divided by x plus 21. So basically I start off by trying to get y by itself and solving for it. And we're trying to get all possible integers for this. That's why we have to do it. We can't just guess and check because we'd have problems. So this is a proper way of doing it. So we do the long division, brief long division. In this case, it's pretty brief for long division, to be fair. But it is the long division algorithm. And you follow these steps. X plus 21, you're dividing that out of 10x plus 228. So you just do the first factor, 10x divided by this leading saying x equals 10, which later implies that 10 times x plus 21 equals 10 times x plus 210, which is what you subtract out of it. Put 10 here and you subtract the 10 times x plus 21. And you get only 18, and that's the remainder since we can't really do any more from here. There's no more leading terms or anything. And therefore y equals 10 plus 18 divided by x plus 21. X plus 21 divides 18. That's basically what we notice from how this is set up. 18 divided by x plus 21. But we can show this briefly. My y equals 10 plus 18 x plus 21 is in z, implies that 18 over x plus 21 is in z, which implies that 18 divided by x plus 21 equals a is in z, which will further imply, we know this factor because y and x are integers. Then it goes down, you take this further into the addition of them, meaning that you have to add two integers together to get an integer, and eventually, in one this times an integer, the other one has to be an integer. Basically, you really want to get into it, but basically you just follow this process. Basically, you get 18 equals x plus 21 times a, multiply across, and that means that x plus 21 divides 18 by definition. That form of you have that classic form. And the next of the basically 4-step plan, I call it step 3. B divides 18 where b equals, I'm basically trying to find all the divisors of 18 here, and I try to do a technical. B divides 18 where b equals all these numbers. And that means x plus 21 divides 18 implies that x plus 21 is in this range, this set of numbers. X plus 21 has to equal this set, one of these numbers from here. Then I subtract 21, or I add negative 21 to the set, so x is in negative 21 plus the set. Then I just add negative 21 to each individual number of the set, and you get x is in this range of values. Yeah. This is not going to be pretty, because now we know all the values that x can be. Good luck solving this if you were given this on a test, I'll tell you that much. I honestly don't think if you have only a short amount of time, you'd be asked this many values. You'd probably be given one with only 6 values, about probably 4 to 6 or something like that. Only a few different ranges, a few different combinations. So you can plug in. Because basically that's what we have to do now. We're going to tabulate them. So for every x value, you have to calculate a y value, and you can use this form y equals 10 plus formula derived from it, where y is equal to that number, that division from long division we figured out, so remainder. You can just use that to figure out these numbers, and that's done for each one until you get the x equals negative 3, which is the last one, 11. And if you double check all of these, they'll work. These x and y values will give you exactly the right hand side. Every one of these x and y values will, together when paired together.